Hi, my name is Sam Hart, and today I'll be presenting on the design and testing of a magnetohydrodynamically pumped liquid metal cooling loop for CubeSats. So first, the motivation. Why are we looking into this wordy and difficult to pronounce technology? Well, the simple fact is that high-power CubeSats are becoming more common. We're seeing these large deployable solar arrays which are being used to power subsystems such as high data rate communications, electric propulsion, and other high-power subsystems. Now, with all this extra power comes an associated heat load. We've already developed deployable radiators to effectively reject that heat out into the space environment, keeping the CubeSat cool. So the remaining question is, how do we get heat to those deployable radiators from the hot components deep inside of the satellite? Well, you've got a number of possible technologies you could use. You can use thermal straps, and now they even come in flexible varieties, which means we could, in theory, directly connect the thermal strap to the deployable radiator. Now, that's great. They're very simple. There's a lot of benefits to thermal straps, but they become quite massive if you need to transfer large amounts of heat, which could be hundreds of watts in a CubeSat, over long distances. The mass adds up very quickly and they become infeasible. So then you might look to heat pipes. Heat pipes are nicer because they can transfer a lot more heat per unit mass. These are very lightweight and they can move hundreds of watts, no problem. There are a couple issues with these though. One, heat pipes are not generally flexible, which means that they can't necessarily directly interface with a deployable radiator in most cases. The next issue is that high-performance heat pipes are very pricey. These are the aluminum ammonia heat pipes. You'll pay a significant sum of money for these. They're usually very custom, and that just may not be conducive to the CubeSat style of satellite. So the next thing you might look at is an MPFL, or mechanically pumped fluid loop. These have a lot of nice benefits. One, they're actively controllable, which is really nice. It means you can ramp up or ramp down the amount of heat you want to transfer. You can turn them on and off when you're in hot and cold periods. They can work with flexible tubing, which is really nice. It means you can directly interface with that deployable radiator. Again, this is very beneficial because you get very direct heat transfer into the radiator. Really, there's lots of benefits to this technology. The only issue is the mechanical pump itself. Because mechanical pumps have moving parts, they're inherently more likely to fail than something simple like a thermal strap, which in the end is really just a big block of metal. And so with that moving part and higher rate of failure, you need some way of getting around that, mitigating your overall failure rate. So what a lot of systems do is put multiple mechanical pumps in parallel. So if one goes out, the rest of the system still works, and your mission doesn't fail as a result of that single point failure. Now, when you add extra pumps, what you get is additional mass, additional complexity, and additional cost, none of which are desirable. So what we'd love to see is a small, reliable device with high heat transfer rates that has all of these benefits of the mechanically pumped fluid loop. And so what our lab is proposing here is a magnetohydrodynamically pumped cooling loop. Now, what this is just like a mechanically pumped fluid loop, except we replace that mechanical pump with one that runs on the Lorentz force. What happens here is we build a pump body where liquid metal is able to run through it. Now, we put copper conductors on either side of that pump body that run a DC electrical current through the liquid metal. Perpendicular to those, we place two sets of permanent neodymium magnets which generate a strong magnetic field in that pump cross-section. So now you have an electrical current crossed with a magnetic field, which gets you a Lorentz force. And that is how we actually pump the fluid through the loop. Now this is beneficial for a couple of reasons. The main one being we have no moving parts at all, which we believe will contribute to a much higher reliability because there's really not much that could fail in here. We're just conducting current through a conductor. So it's a very nice theory, a nice idea, but then the question is, does it actually work? Is this even worth looking into? So let's look at if it is any good, even in theory. So we're going to look at a use case here. Let's say we want to transfer heat 30 centimeters, which is the full length of a 6U CubeSat. Let's say we're transferring that heat into a 20 by 30 centimeter deployable radiator, and we're giving a 1 amp current input. Now, because our pump runs on the Lorentz force, the input current is directly proportional to the output pressure. So that's why I'm listing that 1 amp input current there. Now, one other thing I want to note is that the temperature of the radiator is dictated by how much heat it is dissipating. There's a direct relationship between temperature and heat dissipation in this radiator. So with that said, let's go ahead and look at what we get in theory. So what we're doing here is looking at different liquid metals we could run through the MHD cooling loop and how much heat they could transfer per unit mass. Now, when I increase the mass of the system, what I'm really doing is increasing the diameter of the tubing that's used in the MHD cooling loop. When I increase the diameter of tubing, the tubes get bigger, it takes more liquid metal to fill them, and the system gets heavier. Now, in this very simple model, the only viscous losses we're looking for are in the tubing themselves. We're using Hagen-Poiseuille flow, which is just flow through a straight circular pipe cross-section. So when we increase that diameter, we get less flow resistance and higher flow rates. So with all that said, let's look at some metals. So NaC77 is our highest performing metal here. As you can see, with a system mass of just about 100 grams, we're approaching the radiation limit, which is the most heat that our radiator could give off given the temperature of our heat load. So that's great. We love to see that we're coming up on that with a nice light system. The issue here is that NaC77 is actually quite dangerous. It explodes when you put it in contact with water. Now, this is very problematic for a CubeSat because we're often ride-along payloads, so launch providers may be upset to hear that we want to fly an explosive. Additionally, if it came in contact with moist air, like you might find somewhere like, I don't know, Florida, it could again combust, which would be problematic. So then you might want to look to a safer fluid, like gallium. That'll be our next option we look at. The issue with gallium is that it freezes at 30 degrees Celsius, or about the temperature of the human body, which means that it'll ice up in your radiators in most reasonable flight systems. So it's probably not a very good idea to use gallium in your CubeSat cooling loop. So the next fluid we're going to look at is Gallium-STAN. Gallium-STAN has some nice benefits. It's safe, just like gallium, maybe not quite as safe, but safe. And it freezes at a much lower temperature. We're looking at about negative 19 degrees Celsius here, so a fair bit cooler. Now it does perform a little worse in terms of how much heat it can transfer per system mass, but for not freezing, that's probably well worth it. Now if you need to go even cooler, you can actually look to mercury, which freezes around negative 30 degrees Celsius, so significantly cooler. Again, you just get slightly worse performance. Finally, I want to draw your eye to this linear line at the bottom of the plot. That is the mass of a simple copper conductor being used as a thermal strap and how much heat it could transfer. As you can see, we are far outperforming the copper thermal strap, which we love to see. It means our technology is working well, at least in theory. So then we wanted to model how much power does this system use? What does it take to actually run this thing? So again, we have an analytical model here. What we're doing is we're summing the ohmic losses, so just the losses you get due to running a current across a resistor. And we're also summing that with the pump power, which is the volumetric flow rate through our pump times the pressure head. So what you can see here is all of these liquids will result in a very low pump power. We're looking at milliwatts. You will, however, note that NaC77 is using a lot more power than these other liquids, and you might wonder why. Well, it's about an order of magnitude less dense than these other working fluids, which means for a given system mass, we're getting about an order of magnitude more cross-section in our tubing. What that means is we get much higher flow rates, so with the same pressure head and higher flow rates, we're getting much, much higher pump power. So that's why you're seeing this much steeper curve out of NaC77 than the other fluids. Now, all of this said, NaC77 is still preferable for a flight system if your launch provider allows it. Alright, so we've shown in theory that this thing works very well, but then the question is, in reality, how does it work? How does it do when you build a real physical system and test it? So we went ahead and did just that. We built a prototype pump that you can actually see here. It's quite small, as you can see, only about 3 centimeters tall. It has N52 neodymium magnets in it. They're about 3/16 of an inch, or 4.8 millimeters for our metric audience, so quite tiny. This whole thing is, about yay big. And we wanted to first test what sort of pressure head can we get out of this. Our models say that we're going to get significant pump pressure out of it, but what do we actually get when we take away all those assumptions from our model? So the way we tested this is we rigged up the pump between 2 cylindrical tanks. We measured the hydrostatic column of gallium that we could pump between tanks. And we are using gallium in these tests simply because it's cheap and easy to work with, though admittedly it is not a very good fluid for a flight system. Instead, you'd probably want to use Gallium-STAN or NaC77 as previously mentioned. So let's see how we did. This is a plot of our estimated pressure output, just based on our analytical models, versus our measured pressure output. Now, as you can see, the analytical model is predicting significantly more pressure than we actually got, about 4 kPa, whereas in reality we got a max of about 2300 kPa. 2300 pascals, 2.3 kPa. So it doesn't quite match up. Part of the reason we're seeing this over-prediction is that we assume perfectly perpendicular fields between the electric current and the magnetic field. We also assume that they are uniform, when in reality, neither of these things is actually true. However, it makes for a very simple analytical model, as you can see here. We're saying that our pressure is simply proportional to the input current, the magnetic field strength, and then inversely proportional to the height inside the pump, which is the distance between the magnets. So, while this model does not perfectly predict things, it is linear with current, just like the actual test data is, which means that if we apply just a simple multiplicative correction factor, we can actually overlay our prediction exactly onto the test data, which means that we can then use this model in a lot of trade studies later on. All right, so next let's go ahead and look at our flow rate. Okay, so here you can see our flow rate measurements, again compared to an analytical model. Now I do want to mention that this analytical flow rate model is different than the one you saw originally when we were doing our theoretical predictions. This one actually accounts for pressure losses in the pump geometry, bends and tubing, etc. And what you see is that our measured flow rates line up pretty well with the predictions. The prediction again overpredicts by just a little bit. This could be due to many factors, including just the way we're estimating the flow coefficient of the pump itself. But it's very close, within 20%. As you can see, our flow rates go up to about 4.6 milliliters per second, which is fairly substantial. And this is actually less than what we would expect to see in a flight system. The reason for that is that the flow rate sensor itself actually accounts for about a quarter of our total viscous losses. So we would expect slightly higher flow rates without the sensor in line. But ultimately, this presentation is about heat transfer, not about pumps and how much pressure and flow they can put out, as much as I love talking about it. So then the question is, how much heat can we actually transfer here? All right, and so it turns out that that's actually just proportional to your mass flow rate. So we're lucky that gallium is actually quite dense, and so we have a fairly high mass flow rate, even with our 4.64 milliliters per second we're getting. We could actually transfer upward of 10.5 watts per Kelvin over a distance of 15 centimeters, meaning 15 centimeters there, 15 centimeters back. And this is just based on our measured flow rates. Now, what this really means for us is that if we had a temperature differential of, say, 30 degrees Celsius between our heat load and our radiator, we could transfer upwards of 300 watts. Now, this is more than the current state-of-the-art deployable radiators for CubeSats can actually emit, which means we're able to fully utilize that technology, and we have some room for that technology to grow in the future, either into larger radiators or radiators with a higher emissivity. All right, so now you might be wondering, this thing transfers a lot of heat, it's very simple, it doesn't have any moving parts, doesn't look like there's a lot going on as far as volume either, so where am I paying? Is it mass intensive? And the answer is no, not really. The pump weighs 11 grams. Now, in a flight system, you probably want 2 pumps, because you'll notice they do have permanent magnets on them. And in low Earth orbit, those magnets are going to try to align with the Earth's magnetic field. So what you'll probably want is one set of magnets facing north-south, the other one's facing south-north, and the torques on those sets of magnets will cancel each other out then, so you have no net torque on your spacecraft. So that'll be about 22 grams of pumps total between the two. For our tubing, if we were to use PEEK tubing, which is a flexible plastic, which we do intend to use, it'll weigh just 23 grams per meter. And then finally, gallium itself is just about 100 grams per meter for the diameter of tubing we've been using, which is about 4.76 millimeter diameter. So what this means is that altogether, we're looking at a system mass of less than 150 grams to transfer heat over a distance of 30 centimeters. That being 30 centimeters there, 30 centimeters back, because there's a loop after all, so quite light. But then we wanted to know, can we make the system better? Can we improve on what we already have? So we started looking at pump optimization, specifically looking at how we can optimize the internal geometry of the pump to change the flow rate, the pressure output, and other flow characteristics. So you'll notice these contours. Let's look at the one on the upper right first. This is how much pressure you're getting out of your pump. as a function of the height of the pump, which is the distance between the magnets, and the width of the pump, which is the distance between the electrodes. You can see here that the pump output pressure really just depends on height. It has no dependence on width in this analytical model. Now we've done additional testing that has shown that there is actually a minor width dependence just because of the shape of the electric current lines as the width changes, but it's fairly minor. So based on that alone, you might think, okay, we want a very short pump to get a lot of pressure out of it. Well, then you look at the flow coefficient plot below it. Flow coefficient is really just a measure of how much liquid can we get through this part for a given pressure drop. And so we want a high flow coefficient to get high flow rates. So based on this, you can see we want a large width and a large height. That gives us this really big flow coefficient. So then how do we balance these two things? The flow coefficient would say we want a large height, the pressure would say we want a small height. Where do we lie? What's the optimal height? Well, it turns out that depends on what else is in your system, how many pumps you have, how much current you're putting in, a variety of factors. So we have just one sample use case here. Let's say we're pumping gallium and we are pumping it over a distance of roughly 30 centimeters. Now, let's look at what the optimal height is as a function of the input current. So between 1 amps and 15 amps, we see that our optimal height varies from about 1.8 millimeters to about 2.2 millimeters, with higher currents preferring larger heights. You will notice that that purple curve for 15 amps has a slightly different shape than the others. That's because the flow actually transitions to turbulent in the tubing at that point. So that's why you see that minor bump down in flow rate. Now, the pump we tested here has a height of 2.5 millimeters. So we're still slightly above the optimum, which means we do have room to improve based on our analytical models, which is fun to see. So next, let's look at some work that we've done since we put out this conference paper. First, I want to talk about heat exchangers. So the idea is that we are using liquid metals, which have a very high thermal conductivity, and because of that, we should be able to build a much more compact heat exchanger. So we wanted to analyze a use case and see how much lighter and smaller these really are. So for our use case, this is going to be just like the original theoretical analytical model we talked about, where we're dumping heat into a deployable radiator, we have one pump in line, etc. Here we're going to say we have a fixed flow rate of 5 milliliters per second. That's roughly in line with our test measurement, so a reasonable estimate. Next, we're going to say that the inlet temperature into the heat exchanger is 373 Kelvin, and we're dumping heat into a 0.24 meter squared radiator. And so what this table on the right is showing us is the mass of the heat exchanger, which is just a copper tube, and the mass of the liquid that's filling it. We want to account for that liquid mass because liquid metals are pretty dense after all, so that mass can be significant. So the takeaway here is that liquid metals lead to lighter heat exchangers. We're looking at about an order of magnitude decrease in mass compared to using water. You wouldn't want to use water in the MHD loop for a number of reasons, but it's a convenient fluid to compare to because we're all familiar with water, right? And so if we look at, say, the 150 watt use case, we're dumping 150 watts into this deployable radiator. The gallium heat exchanger weighs only 4.4 grams, while the one built for water has a mass of 142.8 grams. This means that we're saving 138 grams or so of mass by using gallium instead of water in this heat exchanger. Now, on any reusable flight system, you'll have two heat exchangers, one on the hot side, one on the cold side. So we're looking at upwards of 250 grams of mass savings. Now, this is a big deal in a CubeSat because our total mass for, say, a 6U CubeSat would only be 8 kilograms maximum. So this is a big portion of our overall total mass. Now, the next thing we want to look at that we've been working on since putting out this paper is the power processing unit. Our pump performance is directly proportional to our input electrical current. However, CubeSats can only put out about 2 amps in a standard CubeSat bus. This is not a lot of current. In our ideal world, if we want to really get the most out of this pump, we want to be putting out double-digit amps. So how do we do that? Well, we've actually developed a power processing unit that will take a low current input and convert it to a high current output. You can run this off of the 12-volt bus on a standard CubeSat. And as you can see, for about 160 milliamps of current input, we get 12 amps output. This is a big jump in current and allows us to operate the system inside of a CubeSat. Now, the system is very light. It's just 39 grams for the prototype design, which has a lot of debugging features which aren't necessarily necessary in the final design. The system also uses less than 2 watts, and that's while it's running the pump at this 12 amp current input, so a very low power system. All right, and so now I'm going to go ahead and conclude. We've designed a system that can transfer upward of 300 watts max heat transfer rate, and is actively controllable, meaning you can vary your flow rate to increase or decrease your heat transfer as desired. The system uses less than 2 watts of power to pump itself. It's lightweight at less than 150 grams estimated. Now this is based on measurements of a prototype system, so the mass estimate is just an estimate. There are no moving parts, which means that the system will likely have a higher reliability than a mechanically pumped loop. There will also be no vibration in the system, which is advantageous for optical missions. It's easy to route because we can use flexible tubing. It's low cost because, quite simply, there isn't that much going on inside. It's a simple system to build, just some magnets and electrodes, which contributes to a low cost. And we believe this will be ideal for high-powered CubeSats. They need to move a lot of heat over relatively long distances, 30 centimeters being long for a CubeSat. Now, development is still ongoing, and we're working towards developing a flight-like system for use ultimately in space. Real quick, I'd like to acknowledge the National Science Foundation for funding my graduate work, and I'd like to acknowledge Connor Awald for designing, building, and testing the power processing unit. And with that, I'm open to questions. Feel free to shoot them to me at samuelthart@gautech.edu.